the last lecture of this unit on numerical methods, we see an approximate method of finding approximate solutions to a system of linear equations. That is the Gauss-Seidel method, and we will see Rayleigh's power method to find the largest eigenvalue of a matrix and corresponding eigenvector. So let's begin with the Gauss-Seidel method. Now we have already studied Gauss elimination method. This was a direct method of solving a system of equations, and also it led to exact solutions. What we are now looking for are approximate solutions to a system of linear equations. So the method that we are going to study was given by Gauss-Seidel. To explain the method, I will take a system containing 3 equations and 3 unknowns. However, let me mention at the outset that this method could be applied to any other system in which the number of equations is equal to the number of unknowns. So, suppose I have a system of equations containing 3 unknowns, 3 equations and 3 unknowns. Remember, I am only looking for an approximate solution, not an exact solution. Now, for this method to work fine, there are certain assumptions we have to make. These coefficients that come along the diagonal in the coefficient matrix A1, B2 and C3 will form the diagonal of the matrix. These coefficients have to be dominant. That is, as compared to B1 and C1, the value of A1 has to be large. Large as in the sense of magnitude. Maybe this is minus 10, this is 2 and this is 2. So it's possible that A1 is minus 10, B1 is 2, C1 is maybe 3. So A1 is surely not greater than B1 or C1. But modulus of A1, that means if I ignore the sign, then A1 is definitely bigger than B1, it is definitely bigger than C1. So the first assumption that one makes in this method is that the coefficients that come along the diagonal have to be dominant as compared to the other coefficients in that equation. That means in the first equation, A1 has to be much bigger as compared to B1 and C1. In the second equation, B2 has to be much bigger as compared to A2 and C2. And in the third equation, C3 has to be much bigger as compared to A3 and P3. If not, then you can always rearrange some of these equations in such a manner that the dominant numbers come along the diagonal. So one can always rearrange the equations. That's not going to affect the solution. But before applying this method, make sure that you have the biggest coefficients along the diagonal. Okay. Now coming to the actual method. I will write the first equation as x in terms of everything else. In the second equation, I will keep only y this side, transfer everything else to the right hand side. And in the third equation, I will keep only z over here and transfer everything else to the right hand side. So I am looking for an approximate solution to this equation. As I said, in the first equation, let me transfer the other two terms to the right hand side. So I get B1 minus B1y minus C1z. Let me divide throughout by A1. So I get, let me call this as equation 1. Similarly, in the second equation, I'll isolate y. I'll keep y to one side and transfer everything else to the other side. So I get y equal to d2 upon b2 minus a2 upon b2x minus, this term will go to the other side, c2 upon b2z, equation 2. And from the third equation, if I keep z on this side, and transfer everything else to the other side, I'll get minus a3x minus b3y write 2 out by C3, this is what I will get. So the first step is to write the given system of equations in this form, where from the first equation we keep x to one side, transfer everything else to the other side. From the second equation we keep y to one side, transfer everything else to the other side, and in the third equation we keep z to one side and transfer everything else to the other side. Now we are going to start with an initial approximation. I will put x naught equal to 0, y naught equal to 0, z naught equal to 0. This will be my initial guess. So this is where I begin with. In equation 1, we will put y naught equal to 0 and z naught equal to 0. Rather, I will put x equal to x naught. I'll put y equal to y naught, which is 0, and z equal to z naught, which is equal to 0. So in equation 1, that is in this equation, I will put y equal to y naught, which I am taking as 0, z equal to z naught, which I am taking as 0. So that will give me x1 to be d1 upon a1. So I get the value of x1. Now in the second equation, in equation 2, I will put x equal to x1 and z equal to z naught, which is equal to 0. So in equation 2, I am going to make a substitution on the right hand side, and on the right hand side you will notice that I only have x and z. So in this method we make use of the latest values available to us of the unknowns. The latest value of x that is available to us is x1, and the latest value of z that is available to us is still z naught. So in this equation I put x equal to x1, z equal to z1, z equal to z naught, and from there I will get the value of y1. y1 will work out to be d2 upon d2 minus a2 upon b2 into x1, because z naught is 0. Now I know x1, I know y1. Now we go to equation 3. In equation 3, check out what are the terms on the right hand side. On the right hand side I have only x and y, and the latest available values of x and y with me are x1 and y1. So in this equation I will put x equal to x1, y equal to y1, and the value of z that I will get will be z1. So I will get some value of z1 from this equation by putting x equal to x1, y equal to y1. This is the end of iteration 1. At the end of iteration 1, I have x1, y1, z1. So this will be my first approximation to the solution of the given system. Next, I will again go back to equation 1. Look at the terms on the right hand side. On the right hand side, I have only y and z. Always make use of the latest available values of the unknowns on the right hand side. The unknowns on the right hand side are y and z. The latest available values of y and z are y1 and z1. So I will put the values of y1 and z1 in this equation and get x2. Then in the next equation, I will put the value of x2 for this, z1 for this, and I will get the value of y2. And similarly in the next equation, when I put x2, y2, I will get the value of z2. So this will be the end of the next iteration. It will give me the next approximation to the solution of this system. So let us actually start with a few problems and then see how this method works. apply Gauss Seidel iteration method. To solve the following system of equations. X plus 5 plus z equal to 12, 2x plus 10y plus z equal to 13, x plus 5 plus 5z equal to 7. Remember the condition that I mentioned, even before you begin, you have to make sure that the coefficients that you come across along the diagonal have to be large as compared to the other coefficients in that equation. Now, 10 is surely bigger than the other two coefficients that we get. Here also 10 is much bigger as compared to the other two coefficients. And here 5 is much bigger than the other two coefficients. So I don't need to readjust these equations. They are in a perfect form. Now that we have the dominant numbers along the diagonal, let us adjust the system so that in the first equation I have x to one side, everything else to the other side. So my first equation will look like 10x equal to 12 minus 5 minus 10. But I don't want this 10 also over here, I want only x. So let me transfer 10 to the other side. So I rewrite the first equation as x on this side, transfer every other term to the right hand side. From the second equation, let's do the same thing to y. So from the second equation, I'll get 10y equal to 13 minus 2x minus z. And I want to transfer this 10 also to the other side. So that will go as 1 upon 10. Then from the last equation we will get z equal to 1 upon 5 times 7 minus x minus 5. So to begin with, we put x not equal to 0, y not equal to 0, z not equal to 0. That's going to be our initial guess. And we'll start with the equation 1. In equation 1, look at the unknowns on the right hand side. In equation 1, the unknowns on the right hand side are y and z. So we have to put the latest available values of y and z. The latest available values of y and z are y0 and z0. So put y equal to y0, z equal to z0 in equation 1. This is just iteration 1. So let us put y0 equal to 0, z0 equal to 0 in equation 1. We will get x1 equal to 1 upon 10. 12 minus 0 minus 0. So that will be 12 upon 10, which is equal to 1.2. Now come to equation 2. In equation 2, the unknowns on the right hand side are x and z. Remember, we have to put the latest available values of the unknowns. The latest available value for x with us is x1 and the latest available value of z is still z0. So in equation 2, we put x equal to x1, which is 1.2, and we put z equal to z0, which is equal to 0. So if I substitute in equation 2, I'll get the next approximation to the value of y. That is 1 upon 10. It is 13 minus 2 times x1 minus z0. Z0 is 0. If you simplify this, this is going to be 13 minus 2.4 upon 10. This is 10.6. This is 10.6 upon 10. So this will be 1.06. equation. So in equation 3, we put x equal to x1, which is 1.2, and y equal to y1, which is 1.06. So from equation 3, we get z1 equal to, we get z1 to be 1 upon 5, 7 minus x1 minus y1. And here I will give you the calculator value directly. This works out to be 0.948 or something close to that. I think it is 0.948 exactly. So the latest available values with us, the first approximation is x1 equal to 1.2, y1 equal to 1.06, z1 equal to 0.948. This is what we get at the end of iteration 1. Now let us start with iteration 2. For iteration 2, once again we do the same thing. Remember the basic rule. Look at the unknowns that you have. You have to go in this order 1, 2, 3. Look at the unknowns on the right hand side and take the latest available values for the unknowns. So in iteration 2, we have to again start with the equation 1. The unknowns on the right hand side are y and z. Latest available values of y and z are y1 and z1. So in equation 1, put x equal to put y equal to y1, which is 1.06, and put z equal to z1, which is 0.948. So if you substitute for y as 1.06, z as 0.948, the latest available value, you will get x2 as x2 is 0.9992. So x2 works out to be so much. Now go to the next equation. The unknowns on the right hand side in equation 2 are x and z, and the latest available values for x is x2, for z it is z1. So in equation 2, put x equal to x2, which is 0.992, and put z equal to z1, which is 0.948. So if we substitute this in equation 2, we get y2 as, to be 1.00536. Now let's go to the last equation, equation 3. In equation 3, look at the unknowns on the right hand side. The unknowns on the right hand side are x and y, and the latest available values of x and y are x2 and y2. So in equation 3, put x equal to x2, which is 0.9992, and y equal to y2, which is y2 is 1.00536. So if we make the substitution in equation 3, we get z2 as, to be 0.999544. So at the end of iteration 2, we get x2 as 0.9992. Then we get y2 as 1.00536, and we get z2 as 0.999544. In the previous step, we had got z1 as 0.948. This is 0.9 something. So at least up to the first decimal places they match. Look at y2. y2 is 1.00536, whereas y1, I had written out y1 somewhere. y1 is 1.06. So again, y1 and y2 at least match in the first decimal place. And x1 x1 was 1.2, where x1 and x2 are not too close. So some more iterations will be required. Probably you may have to perform 2-3 iterations more. It all depends on what is the degree of accuracy that has been demanded. So depending on how many decimal places you require, accordingly you carry out that many iterations. Sometimes they may specify the number of iterations. So at the end of that iteration, whatever answer you get, you take that as the approximate solution. So this is how we get an approximate solution to a system of linear equations. I have done the theory as well as the problem for a system of 3 equations and 3 unknowns. But you could as well apply this to any other system, provided of course number of equations is equal to number of unknowns. Let's go to the next method now, that is Rayleigh's power method to find the largest eigenvalue of a matrix. We are now going to study the power method to find the largest eigenvalue and corresponding eigenvector of a matrix. In the unit on linear algebra, we have already studied what are eigenvalues and eigenvectors. Let me quickly recall the definition. Suppose A is a square matrix of order n. A scalar lambda is called an eigenvalue of A. Lambda can be either a real number or a complex number. So a scalar lambda is called an eigenvalue of A if there exists a non-zero column vector x. If there exists a non-zero column vector x such that Ax is equal to lambda times x, and there will be infinitely many. If at all there is one such vector, you can be rest assured that there will be infinitely many such vectors satisfying this equation. Each such vector will be called an eigenvector of A. It's an eigenvector of A corresponding to the eigenvalue lambda. I had explained earlier in that unit why the eigenvector is never allowed to be 0. However, the eigenvalue can be 0. So, by definition, an eigenvector is never allowed to be the 0 vector. So, a scalar lambda will be called an eigenvalue if we can find a non-zero column vector for which this equation is satisfied. Now, if you recall, the simplest way to find the eigenvalues of a matrix is to solve the characteristic equation of the matrix, and the characteristic equation was given by determinant of A minus lambda I equal to 0. So in order to get the eigenvalues of a given matrix, it's not always going to be possible to sit and search for lambda and for x. So this is a mechanical way of finding the eigenvalues. Simply solve the characteristic equation of the matrix. The characteristic equation is given by determinant A minus lambda I equal to 0. And if we expand this, all this we have done earlier, this is a polynomial in lambda of degree n. And a polynomial of degree n must have exactly n roots. That's why a square matrix of order n will have exactly n eigenvalues. So once you have got the eigenvalues, then for each eigenvalue separately solve the homogeneous system A minus lambda I times x equal to 0. If lambda is an eigenvalue of A, this homogeneous system will have infinitely many solutions. non-zero solution. Any non-zero solution to this system is going to be an eigenvector corresponding to the eigenvalue lambda. So this is the precise method for finding eigenvalues of a matrix and eigenvectors corresponding to several eigenvalues. However, now we are looking for a method of finding an approximate value of the largest eigenvalue. So let me explain the method again for a 3 by 3 matrix. So suppose I take A to be a square matrix of order 3. So as I mentioned over here, it will have 3 eigenvalues. Let me take the 3 eigenvalues to be lambda 1, lambda 2, lambda 3. So if I start with the square matrix of order 3, it will have 3 eigenvalues, lambda 1, lambda 2, lambda 3. And let me take x1, x2, x3 as corresponding eigenvectors. So ax1 will be lambda 1 x1, ax2 will be lambda 2 x2, and ax3 will be lambda 3 x3. x1 is an eigenvector corresponding to lambda 1, x2 is an eigenvector corresponding to lambda 2, x3 is an eigenvector corresponding to lambda 3. So these equations will be satisfied. Now take any column vector which is a linear combination of x1, x2 and x3. You are free to choose whatever values you want for these scalars k1, k2, k3. So take x to be any such linear some constant into x1 plus some constant into x2 plus some constant into x3. Now let us compute the product a into x. If I take the product ax, let me first substitute for x. It is k1 x1 plus k2 x2 plus k3 x3. Matrix multiplication is distributive over addition. So when I open out the brackets, I get a times k1 into x1 plus a times k2 into x2 plus a times k3 into x3. Now the scalar has the freedom to move in the product. So I could write this as k1 times ax1 plus k2 times ax2 plus k3 times ax3. But then I know what is ax1, I know what is ax2, and I know what is ax3. So let me substitute. I'll get k1 times lambda 1 x1 plus k2 times lambda 2 x2 plus k3 times lambda 3 x3. So this is a times x. Let me again calculate a square times x. Why I am doing this will be clear very shortly. So till then bear with me. Let me calculate a square x. A square x is a into ax. A square is a multiplied by a. Matrix multiplication is associative. So it doesn't really matter where I put the brackets. And I know what is ax. I just now calculated ax. Here's ax. So let me substitute for ax. Ax is k1 lambda 1 x1 plus k2 lambda 2 x2 plus k3 lambda 3 x3. So a square x will be, let's open out the brackets. A k1 lambda 1 x1 plus a k2 lambda 2 x2 plus a k3 lambda 3 x3. And remember the scalars have the freedom to move. So I can write this as k1 lambda 1 ax1 plus k2 lambda 2 ax2 plus k3 lambda 3 ax3. But once again we can substitute for ax1, ax2, ax3. ax1 is lambda 1 x1, ax2 is lambda 2x2 and ax3 is lambda 3x3. So I get a square x as k1, lambda 1 into lambda 1 becomes lambda 1 square x1 plus k2, lambda 2 square x2 plus k3, lambda 3 square x3. So a square x looks like this. Now, if you don't really want to waste time, you will have to accept my word for it that the r power. If we continue in this manner, the r power is going to look like k1 lambda 1 raised to r x1 plus k2 lambda 2 raised to r x2 plus k3 lambda 3 raised to r x3. So if I continue like this, I will get ar into x as this. Now out of the three eigenvalues lambda 1, lambda 2, lambda 3, suppose in magnitude, that means after ignoring the sign, suppose lambda 1 is the greatest eigenvalue. Suppose lambda 1 is greater than lambda 2, lambda 1 is also greater than lambda 3. So out of the three eigenvalues, suppose lambda 1 in modulus is the greatest eigenvalue. If this is greater than lambda 2, this is greater than lambda 3, then as we take higher and higher powers of lambda 1 square will be much bigger than lambda 2 square, lambda 1 square which will be much bigger than lambda 3 square, and the difference will become even more when I take cube. The difference will become even more when I take the fourth power. So as I go on taking higher and higher powers, this lambda 1 raised to r is going to be much bigger as compared to lambda 2 raised to r and lambda 3 raised to r. It's so much so that this term dominates the whole of the right hand side. So as compared to the other two terms, this will give a major contribution to the right hand side. So I can say that this will work out to be something like, and for the sake of convenience, just so that we don't have to deal with that scalar k1, I mentioned that the choice of the scalars is in our hands. I take k1 as 1. Because if I take k1 as 1, I don't have to bother with that complication. I'll get arx equal to, I'm taking k1 as 1, so I'll get lambda 1 r x1. So as I go on taking higher and higher powers, notice that arx will come very close to this, and this x1, if you remember, it is an eigenvector corresponding to lambda 1. Lambda 1 was the largest eigenvalue of the matrix A. So if I continue doing this, a stage will come where I will be very close to the eigenvector x1. So this method gives me an idea as to how to get an approximate value of the eigenvector x1. So with this much background information, let me tell you how the method is going to work. And then I'll illustrate it with the help of an example. So suppose I have again, let me take a square matrix of order 3, and suppose the largest eigenvalue of this matrix, is lambda. And let x be a corresponding, see I am very careful, I always say a corresponding, because for the same eigenvalue there can be infinitely many eigenvectors. So take any one of them as an eigenvector, let x be a corresponding eigenvector. So suppose lambda is the largest eigenvalue and x is a corresponding eigenvector. I am only interested in finding an approximate value of x and an approximate value of lambda. So we will start with an initial guess x1. Now since we need to begin somewhere, for a 3 by 3 matrix, we generally take x1 to be, for a 2 by 2 matrix, you can take x1 to be 1, 0, because there the column vector will have to have just 2 rows. So we will take this as the initial guess. We will calculate the product AX1. Calculate the product AX1, and on the right hand side you will get a column vector, because A is 3 by 3, x1 is 3 by 1. So when I multiply them, I get a matrix of order 3 by 1, which is a column vector. So when I multiply these two, I get a column vector. I am going to normalize that column vector and write it as normalize means what I will do is, whatever column vector I get on the right hand side, look for the largest number over there and take it outside the bracket. Because if you take it outside the matrix, so that the largest number that you will have in the column vector will be 1. This again will be clear when we actually do the problems. This will be called first approximation to lambda, the eigenvalue, and this will be the first approximation to the eigenvector. In the next step, I will do this into this vector. And once again I will get a column vector. Again I can put it in the form. So this will be my next approximation to the eigenvalue, next approximation to the eigenvector, and so on. I will get A1, R approximation, and prior to this the step will be Ax1 r minus 1 equal to lambda raised to r x1 raised to r. I continue this till the difference between these two eigenvectors is negligible or as small as I want. So x1 raised to r should be almost the same as this. So once this difference is negligible, this quantity is going to be the same as this quantity will be the same as this. So we can say that this number that we have is an eigenvector, and this will be the largest this will be an eigenvalue, and this will be the largest eigenvalue of the matrix A, and this will be a corresponding eigenvector. So let's try out the problem. Find the largest eigenvalue and a corresponding eigenvector of the matrix A equal to we are interested in only the largest eigenvalue and a corresponding eigenvector of that eigenvalue. So let lambda be the largest eigenvalue of A. And x be a corresponding eigenvector. I need to begin with an initial guess. As I said, I will always begin with 1, 0, 0. So let x equal to 1, 0, 0 be an initial guess. Let us calculate the product A into x. Let us calculate the product A into x. That will work out to be a column vector. So look at A times 1 minus 1, 2 3 minus 1, minus 2 1 5 into x. X is 1 0 0. Now it should not be difficult to multiply these two matrices because these two entries are zeros. So it should be 4 2 minus 2. Now let me tell you what I meant by normalizing. Look at the largest element. And when you are looking at the largest number, don't bother with the sign. Out of all these, the largest number is 4. In magnitude, take that outside the matrix. So this will be 1. 2 upon 4 will be 0.5 and this will be minus 0.5. So this way, in this matrix, the largest number that I will get is 1. So we will say that this is my first approximation to the largest eigenvalue and this is my first approximation. Whatever number we get outside, that is the first approximation to the largest eigenvalue and this matrix will be the first approximation to a corresponding eigenvector. Next, we are going to multiply A with the latest available eigenvector. So this is my first approximation. Next, we compute the product A into x1. So that will be 4 1 minus 1 into x1. x1 is 1, 0.5 minus 0.5. Do the calculations. I've already done them. This will work out to be 5 4 minus 4. Now remember what should be done. Take the biggest number outside the matrix. Forget the sign. Out of these three biggest numbers, 5, take that outside the matrix. So we get 1. 4 upon 5 should be 0.8 minus 0.8. Whatever number you get outside the bracket, that is the next approximation to the eigenvalue, largest eigenvalue. So my second approximation to the largest eigenvalue is 5 and second approximation to a corresponding eigenvector is 1, 0.8 minus 0.8. This is the second approximation. They are not very close because if we look at the first approximation and the second approximation, first approximation is 4, second approximation is 5. I must continue this till the successive difference becomes really small. So next step will be take this as the next approximation. So A into x2. When I multiply these two matrices, I got the product with me. This is in fact, I have also adjusted it because I have also taken the constant outside. So I will give you that product directly. It is 5.6 into 1. I think this is so this is the third approximation to the largest eigenvalue and this is the third approximation to corresponding eigenvector. Well, now at least we are getting somewhere because from 5 the next eigenvalue that I have got is 5.6. So maybe we are getting close to the largest eigenvalue. Let me just do one more step. In the next step, we multiply A with x raised to 3 and this time after bringing that constant out it becomes 5.8571428 into 1 minus 0.8. We have now come to 5.85. Not bad. And one has to continue this till the desired degree of accuracy is reached. I'll give you the actual largest eigenvalue and the corresponding eigenvector, and you all could continue this for a few more iterations. The largest eigenvalue is 6. One can actually do this by our usual methods, find the 3 eigenvalues and pick the largest. The largest one in this case is 6 and corresponding eigenvector. So if your answer is anything close to this, then we are working in the right direction. So it's all a matter of now computations. There isn't much to it. You just need to have the patience, make sure that all your calculations are right, and depending on what degree of accuracy is required or maybe number of approximations is specified, accordingly you give the approximate largest eigenvalue and a corresponding largest eigenvector. With that, we are done with this unit on numerical methods. That